Hello, my name is Abraham Haitley, and today I will be presenting the work me and my collaborators did looking at developing new privacy controls for smart speakers. Smart speakers, such as the Amazon Echo Dot, are amazing products. These are interactive speakers that allow users to search for information online, order products online, and control Internet of Things devices in the home, all through simple voice commands. However, they raise many privacy concerns about how a user's voice commands are stored, managed, and what may be learned from listening in on people's homes and conversations. Many smart speakers address this by having privacy controls. However, existing privacy controls suffer from issues and flaws. Perhaps the most commonly used privacy control is the activation keyword. The way this works is that instead of a smart speaker's microphone streaming everything it hears to a manufacturer's backend, audio is processed locally on the device until an activation keyword, such as Hey Google or Alexa, is heard. While this may seem to solve privacy concerns, there is the obvious danger of accidental activation, when the keyword is used in ways that are not meant to activate the device, or a user says something that sounds similar to the keyword. This means that conversations the user may want to keep private are not kept private. The other privacy control is the mute button, a button on the device that a user presses when they want to deactivate the smart speaker's microphone. Whilst on paper this solves the problem of accidental activation, in practice mute buttons suffer many usability issues and are often not used. The mute button is inconvenient to use in instances where a user is far away from the smart speaker. It is especially difficult to use in cases where a user wants to interact with the smart speaker and simultaneously have a private conversation with friends, such as if they are using a smart speaker to play music during a party. To properly use the smart speaker, the user would have to talk to the smart speaker, walk up to it, mute the smart speaker, walk back to their friends, say something to a friend, need to interact with the smart speaker, talk to it, forget that they muted it, sigh in frustration, go up to it, turn it on, talk to it, mute it, go back, and repeat the whole cycle. All of which can be extremely frustrating. As a result, many users opt to leave their microphones of their smart speakers in an unmuted state. These always-on microphones are thus always listening in. Coupled with the potential for false activation, this means that private conversations may get streamed to manufacturers' backend. So this had us thinking, what would better privacy controls look like? To solve the problems of existing controls, they would have to be easy to use, intuitive, and easily detect when they should be on and off, without too much effort on part of the user. And the answer we came up with was interpersonal communication cues. To give an example of interpersonal communication cues, take a look at this picture. Even though it is a still image, you can probably tell who is interacting with whom and who is talking to whom. The two people on the right are talking to each other, the people in the far back are interacting and talking to each other, and the person on the left isn't talking to anyone and is on their phone. You could probably tell this by seeing where they were looking at, their hand gestures, their body posture. And that is the power of interpersonal communication cues. Little nonverbal cues, such as where we are looking at, the volume of our voice, our hand gestures, to communicate who we are talking to and who we are not talking to. And so this begs the question, if smart speakers could pick up on some of these cues, could they tell when they're being addressed? Can smart speakers leverage these cues to know when they are being talked to, and only unmute the sensitive microphone then? From what the literature says, this approach could work. We know that interpersonal communication cues are common, and most people use them fairly consistently. They vary across culture and location, but within a given cultural context, people use these cues fairly often and consistently when conversing with one another. At the same time, some literature suggests that users anthropomorphize their smart speakers. When they talk to the smart speakers, they treat them like human beings. So, if human beings use interpersonal communication cues to talk to each other, and if people treat their smart speakers like human beings, then maybe users could easily adapt to using these cues when talking to smart speakers. Potentially, these cues can be detected, and so, with very little effort by the users, the smart speaker could detect when it is being talked to or not, and so know when to turn its microphone on or off. So that is what our paper investigates. We examined whether interpersonal communication cues can be used as smart speaker privacy controls. We divided our work into 3 tasks. First, we created these smart speaker controls based on interpersonal communication cues. Next, we evaluated these controls to gauge their performance and usability. Lastly, we discuss what we learned through this experience about privacy controls and interpersonal communication cues. When we present today, we don't want the takeaway to be that the privacy controls we created are the best ones ever, or that this is the only way to create privacy controls. Rather, through this study, we highlight what are the opportunities and challenges of this approach and what can be learned in moving forward with developing new types of privacy controls. So first things first, creating the privacy controls. To do this, we needed to know what interpersonal cues to use and how they might look like in a privacy control. We settled on two different privacy controls. The first one we wanted to use is voice volume level, so how loudly you're talking. Voice volume level is used to tell who you're talking to. A whisper means private conversation. Talking loudly, addressing the room. A privacy control based on voice would look like having a decibel meter to detect how loudly a person is talking. And once a threshold is reached, the smart speaker's microphones become unmuted. The other interpersonal cue is gaze. Gaze direction is used to know who you are talking to. You generally look towards those you are talking to. A privacy control with gaze direction would use a camera to turn on the smart speaker when you are looking at it. When you are looking away, the smart speaker's microphones turn off. To implement these controls, we first needed a smart speaker. We created a custom smart speaker prototype that emulated the behavior of an Amazon Echo Dot, using a Raspberry Pi, Amazon Voice Services, and the custom 3D printed case. So that is the smart speaker we created to have our controls. And how do the controls actually work? How does the voice control system work? The setup involves a user, a low-fidelity microphone that can only detect volume level, and our custom smart speaker. The low-fidelity microphone is linked to the smart speaker's microphone to selectively turn it on and off. If a user is speaking softly or not speaking at all, the low-fidelity microphone is not activated, meaning the smart speaker's microphone is not activated. Our device had LED lights to indicate its status, so when the system is not activated, the LED lights would be red to indicate this. When a user speaks loudly, the low-fidelity microphone detects the increase in volume level and unmutes the smart speaker's microphone once the volume threshold is reached. The speaker's LED lights turn to green. To clarify, this does not mean that the smart speaker is activated. It means that its microphones are unmuted. The wake word still needs to be heard. If the user says the wake word loudly, the smart speaker detects this and responds to the user. Its LED lights turn blue. User can then interact with the smart speaker normally, and once the interaction is over, the system resets. The LED lights return to red. What about gaze? We start with a similar setup to the voice privacy control, except that now we have a camera that can detect gaze direction to know when the user is looking at the smart speaker. If the user is looking away, the camera detects this and does not activate the smart speaker's microphones. If the user looks at the device, the camera unmutes the smart speaker's microphone. Again, just the microphone is unmuted. The smart speaker still needs to hear the activation keyword. Once the wake word is detected, the smart speaker is activated. User can then interact with the smart speaker normally, and then once the interaction is over, the system resets. So now on to part 2, evaluating and testing out these new controls. We tested 2 metrics: performance, how well the device worked, and the usability and ease of use of the device. We tested them in 2 separate studies. The first metric was to test whether the controls impact smart speaker performance. Given that our device and our controls first need to detect an interpersonal communication cue before activating the smart speaker, we wondered whether this may impact performance. In other words, whether it impacts a user's ability to activate the smart speaker when desired. We wanted to test our new privacy controls against a mute button control and against a standard Amazon Echo Dot. In the interest of time, I will not be going into too much detail over this evaluation. Those details can be found in the paper, but I will go over our results. In short, we had participants stand at different distances and activate the device, seeing how many attempts it took to activate the device. Overall, we'll see that although the Amazon Echo Dot smart speaker outperformed our controls, The voice control and gaze control perform similarly to the mute button, i.e. the control condition on the graph, which suggests that the disparity is due to the fact we had a custom-built smart speaker rather than anything inherent in the controls. In short, we find that our controls do not hinder performance and do not hinder participants' ability to activate the smart speaker. Now, on to evaluating the usability of these controls. To evaluate this, we constructed a series of tasks for participants to go through where they would use a smart speaker to get a sense of how easy the controls were to use and what users thought about it. The evaluation proceeded as follows. We had participants work in pairs to complete several tasks. Each task had an overall goal, such as booking a table at a nearby restaurant. In the task, we wanted to have participants interact with each other, but also interact with the smart speaker to see if participants could easily change the microphone state. During the task, participants were first introduced to the privacy control they were tested and allowed themselves to familiarize with the device. For each task, there were portions where the participants talked among themselves. So, for example, when booking a restaurant, participants were instructed to discuss among themselves what type of restaurant they would like to go to. Importantly, during these portions of the task, participants were instructed to ensure that this conversation remained private and that the smart speaker's microphones were muted during this portion of the task. There were also portions of tasks where participants interacted with the smart speaker to complete the task. For example, once a type of restaurant was chosen, participants interacted with the smart speaker to get a list of nearby restaurants that matched their criteria, such as Thai restaurants. There were 3 such tasks participants completed in total, one for each of the 3 conditions. 2 of these conditions were the voice privacy control and the gaze privacy control, and the 3rd condition was a physical mute button to compare how our privacy controls compared to existing privacy controls. While participants were completing the tasks, a researcher was observing the experiment, and to gauge usability of the controls, we collected various data points. We measured the usability of the controls through the system usability scale and the ranking exercise. We measured how effective the controls were by measuring how often participants were able to keep the smart speaker microphone muted when it was meant to be muted. Additionally, we asked participants open-ended questions about what they thought about the controls, what they liked, what they didn't like, etc. Now for our results. The first result is that in terms of usability, the voice privacy control and the standard mute button were found to be equally usable. Here the y-axis shows the usability score on the system usability score scale. The higher numbers mean more usable. We see that the voice control and mute button have similar usability scores. This usability is validated by the ranking exercise and the interviews. Participants were asked to rank the different privacy controls based on usability. The most common ranking was voice, followed by gaze, followed by mute button. And in the interviews, participants often commented on how easy and natural the voice control was to use. These results combined suggest that the voice was perceived to be as, if not more, usable than the mute button. And although participants also liked the gaze condition, they did express concerns, and overall found it to be less usable than the voice control. Particularly, with the gaze condition, participants highlighted 3 main concerns. First, some participants ranked it low on the usability because of limitations of needing to look at the camera. In our experiment, this meant that they had to position themselves in a certain way to look clearly at the camera and angle the head just right to get it to work, which meant that it was sometimes difficult to activate. Hypothesizing beyond the experiment, participants worried about what would happen if they are in a different room than the smart speaker or otherwise were in a situation where they couldn't look at the smart speaker. Another cause for concern was the lack of visual feedback. Our smart speaker, similar to existing smart speakers, had LED indicators to indicate status updates. Red means that the device's microphones were muted, green meant that the smart speaker's microphones were unmuted, and blue that the smart speaker was interacting with the user. This was used to tell when the microphone was muted or unmuted. With the gaze condition, participants couldn't verify that the microphone was turned off. The nature of visual feedback meant that one needed to look at the device to confirm the device was muted, an act which in of itself unmuted the device. This lack of feedback was concerning and made the control not easy to use since you could never really tell if the microphone was muted. Lastly, there was the concern of having an additional sensor, the camera. participants felt they traded visual privacy for audio privacy. So that's about usability, how easy and comfortable the controls were to use. But did the controls work? Did they keep the smart speaker microphone quiet? In short, yes, and better so than the mute button. So if you remember, the tasks had portions where participants were instructed to talk among themselves and to keep the conversation quiet from the smart speaker's microphones. For each task, we measured what percentage of the time during which the microphones were supposed to be muted were they actually muted. This graph shows the results. A 1.0 means 100% of the time that the smart speaker microphone was supposed to be muted, it was. So the higher the number, the better able participants were at keeping conversations quiet. Here we see that for both voice and gaze, participants were able to keep the microphone muted most of the time. For the mute button though, there was a lot of variability, with participants often forgetting to press it or pressing it too late. Thus, they were less able to keep conversations quiet with the mute button. What's scary to think about is that this was done in a context where participants were explicitly told to keep the conversation muted. In a context where this is not brought up explicitly, the failure rates may be much higher. So those were the main results. Now to move on to asking, what did we learn about using interpersonal cues as privacy controls for smart speakers? First thing that we learned is that these interpersonal communication cues show promise. With the voice condition, and even with the gaze condition, participants were easily able to keep the smart speaker microphone muted. Participants described the voice condition as being easy and intuitive to use. These controls show promise and have the potential to be used more often and more effectively than mute buttons. It is worth exploring the use of such cues as privacy controls for other smart devices in other contexts. However, some things need to be taken into account. First is that if interpersonal communication cues are to be used as privacy controls, they must match the context and situation they are in. There are scenarios and circumstances where the controls work very well, others where they do not. For voice, it is impractical to use in loud environments, where loud background noise would surpass the activation threshold, meaning the privacy control would not be effective. For gaze, it is impractical to use if users are constantly going to be out of sight and range and the smart speaker will not be able to look at it directly. There are several ways to approach this. One is to have controls be customizable. So in a voice volume privacy control, allow users to set what the volume threshold is for activation, so they can account for their own loud voices and ambient background noise. Another thing that can be done is that privacy controls could be combined to reduce the chances of false activation and provide several avenues by which to interact with smart speakers. For example, you could combine the voice volume privacy control with a wake word and with a mute button. Thus, if a scenario appears where one control fails, another control makes up for it. Another thing to take into account is the need for adequate feedback to know when the smart speaker's microphone is muted or unmuted. One of the issues people had with the gaze control, and one of the reasons people liked the mute button, was because of the feedback provided. People feel more comfortable if they know when a microphone is unmuted or when it is muted. With this in mind, if new privacy controls are to be developed, there need to be ways of informing users of the exact state of the smart device. This would require some work to know what an optimal feedback mechanism is, maybe an ambient noise or hum to indicate microphone activity. Lastly, many participants talked about privacy concerns with the new controls, which raises a paradoxical question. To use interpersonal cues as privacy controls, you need a sensor to be able to measure these controls, a sensor which in of itself raises additional privacy concerns. There is a fine balance to strike between measuring interpersonal cues and not creating additional risks. Options need to be developed that strike this right balance. One way is to use low-fidelity sensors that are limited in capabilities to then trigger higher-fidelity sensors. So for example, a decibel meter that can only detect volume level used to activate a more sensitive microphone that can process words and commands. Another option is to only leverage already existing sensors, so there are no additional sensors and no additional privacy violations. For example, many participants were worried about the gaze condition, since it added an extra camera into their home. Thus, this form of privacy control would only be used for smart speakers that already incorporate a camera, such as a Facebook portal or an Amazon Echo Show. So to summarize, in our study, we investigated whether interpersonal communication cues can be used as privacy controls. We find that they show promise for being easy to use and effective at keeping the microphone muted when it is not meant to be used. And we highlight challenges and opportunities that inform the development of future privacy controls. Thank you.